Hi, we are Group 19, and this is our Sentry Equipped Environment Monitoring System, S.E.E.M.S. My name is Danny Rodriguez, and I'm an electrical engineering major.
My name is Esperanto Elbon II, and I'm a computer engineering major.
My name is Noah Rooks, and I'm an electrical engineer.
My name is Peter Abase, and I'm a computer engineer.
Environmental security is a growing concern in today's society, and it's important that we're able to monitor air quality, gas leaks, and other environmental factors. For our S.E.E.M.S design, we are able to capture visual monitoring through our camera, and we have a suite of sensors for environmental data collection. We're able to have real-time status reports of the environment. Monitoring one's environment has become an increasingly important capability. Environment refers to interior areas like homes, schools, and labs. We have monitoring methods range from simple to highly sophisticated solutions. Here's our basic goals and objectives. For S.E.E.M.S to function effectively, the Sentry and its partner application must work seamlessly together, with the Sentry using its cameras and sensors to monitor the environment in real time. Here for our advanced goals and objectives, the Sentry and its partner application collaborate to provide real-time monitoring and data transmission, with streaming live video and sensor data on temperature, air quality, and motion detectness. Here's our stretch goals and objectives, and in regards to time, we will move forward through our presentation. Here we have our table of engineering specifications. For our system requirements, we have 7 requirements. We have tested temperature for our environmental sensor, noise for our microphone, and frame rate for our camera.
The choice of our camera model narrowed down to the ESP32 cam, Hardware Cam Mini, and the Pixie 2 camera. Our reasoning for going with the ESP32 cam was the main interface that the ESP32 camera had, which included a Wi-Fi and Bluetooth integration within the ESP32 board. Given that we're also using the ESP32 as our main microcontroller of the board. In our addition, our camera design is meant to be active only when the Sentry robot is active, or when the sensor alert is triggered, rather than a 24/7 surveillance. The ESP32 cam had a variety of choices within its lens design to choose from. The decision came down to the OV5640 cam model, since it provided much higher resolution and better image quality than the default cam module that came with the ESP32. Choosing a programming language and an environment to build came primarily down to knowledge and comfortability in the workspace of the language environment. The selections narrowed down to React Native, Flutter, Swift, and Kotlin. Although Flutter is on the rise and seen as an attractive option to learn, we chose React Native with JavaScript and TypeScript as our main programming framework for our mobile application. Swift and Kotlin can be developed in their respective platform and exclude us from implementing the app in a cross-platform format.
Here we have our pressure sensor table comparison. It compares 3 different types of pressure sensors, our MS5611, our BME688, our BMP180. Here we have our humidity sensor comparison table. We are comparing 3 different sensors, the BME688, DHT22, and our SI7021. Here we have our temperature sensor comparison table. We're comparing 3 different types of sensors, our TMP36, DS18B20, and our BME688. As seen from the previous tables, we decided to go with the BME688, which tests for pressure, humidity, temperature, and gas. It ensures a safer environment by monitoring air quality.
In the selection process for our present sensors, we end up going with the ultrasonic sensors. This is because of their compact design and affordability. When selecting which ultrasonic sensor to use, we found 3 good options. Despite the advantages of the others, we still decided to move forward with the HC-SR04, as we already own several units, so with its availability and simplicity, it was a clear choice to select. Electric microphones convert sound via diaphragm movement into analog signal. We decided to use them as they met our performance needs without unnecessary complexity of S.E.E.M.S microphones. Although with more time and experience, we believe we can make great use of S.E.E.M.'s compact size and durability. For our microphone selection, we initially chose the S.E.E.M.6542PF microphone, but after issues with the ADC readings, I ended up selecting the SEN0232 analog sound meter for its adaptability.
The right processing unit for the S.E.E.M.S needs to be able to handle connecting to all the sensors and peripherals previously discussed, have the resources to handle data collected from them, and be able to provide the means for reactions quick enough to guarantee both Sentry safety and quick user alerts to CenturyLink. The potential complexity of the path planning algorithms for the Sentry warranted consideration of single board computing, as certain algorithms require a lot more processing power than others. And so, the S.E.E.M.S processing unit initially consisted of one MCU and one SBC. The ESP32S3 was chosen as the system's primary MCU, and the Raspberry Pi 4 Model B was chosen as the system's primary SBC. Before finalizing the decision on processing unit composition, a decision on which movement algorithm to use was made. This will be discussed in further detail later in the presentation, but for right now, it should be known that a simple random walk was chosen. Almost any MCU can manage the overhead of this algorithm, and so the Raspberry Pi 4 was deemed unnecessary. On the ESP32, the most attractive features are integrated Wi-Fi and Bluetooth. These things are foundational to project success for connection to CenturyLink. The inclusion of a camera interface and native support for AI acceleration also make it a prudent choice considering system goals of working with the camera. We ended up choosing the N8R8 due to its high memory capacity and the high likelihood that our code would take up a lot of space. Mobility is probably the largest differentiating factor between S.E.E.M.S and similarly placed systems. This necessarily calls for choosing motors. The deciding factors between the three types considered here were cost, availability, and complexity. Though brushed motors are noisier, less efficient, and less precise than stepper motors and brushless motors, they are infinitely more available, a lot cheaper on average, and much simpler to use. The precision of steppers isn't required for movement, and brushless motors require extra hardware in the form of electronic speed controllers. Given the importance of mobility to the projects, ease of implementation is appetizing as well, as it will help us get the Sentry up and moving quicker. We originally selected the Adafruit TT motors as they were cheap and fit our requirements. Hidden in their datasheet, however, was a small yet powerful statistic on the stall torque of the motor. Stall torque is the amount of torque that a motor provides when it is stalled or not moving. As a rule, a motor's stall torque should be significantly greater than its operating torque. Adafruit listed this motor's stall torque as 78 milliNewton meters, just about 8 times lower than the maximum torque listed in the same datasheet. Suffice it to say, these motors wouldn't move anything but a very light model of the Century, so new motors were needed. We used the mass of a similarly placed mobile robot as an estimate, and we added 30% margins for safety and error. We also included the effect of 3 wheels in the numbers because in a differential drive configuration such as the Century is using, there are 2 drive wheels powered by motors and 1 caster wheel, and they all share the same weight equally. At the end of it all, the Pololu 25D motor with a 75:1 gear ratio and encoders was chosen to drive the Sentry. This motor satisfies all of our requirements, including voltage, current, and speed. The manufacturer, Pololu, provides a much more comprehensive datasheet than Adafruit does for our previously chosen Dudova motor. Our torque requirement is roughly equivalent to 31 kilogram millimeters on this graph. Marked on this graph are the 2 points of interest for us at our desired torque, less than 1 amp of current consumption at approximately 750 milliamps, and greater than 95 RPM at approximately 117 RPM. These motors are actually perfect for S.E.E.M.S. The only issue is that the potential to draw greater than 1 amp of current. This can be managed in software and will be explained later. Also, the encoders are to help with finer speed management. Further examining the behavior of brushed DC motors, the need for a motor driver becomes apparent. Without one, a brushed DC motor spins at a speed proportional to its supply voltage, and it spins in only one direction unless the terminals are manually switched. A motor driver allows for both speed and direction to be more precisely controlled, and this is important for Sentry movement capabilities. It should be able to move left and right, and to move forwards and backwards, so as to allow it to cover the environment properly. Looking at the motor drivers available, the only valid choice were H-bridges. They use transistors and so respond quickly over their mechanical relay counterparts. They provide speed control via PWM and bidirectional control through their structure. Further, H-bridges are really the only proper choice to do anything robotics related. The most important parameters for motor driver selection are driver operating voltage and driver continuous output current. The operating voltage should be able to accommodate the supply needed to power the motors, and the driver should be able to handle the motor stall current. Motor stall current is the current a motor draws when it is stalled. It is important that a driver be able to handle this at 2 points in a motor's normal operation. At the beginning, when a motor starts up, because it will momentarily draw its rated stall current as it starts to overcome its initial resting state, and at any point when a motor stalls and it becomes unable to move. The Toshiba TB9051 FTG is an automotive motor driver with exactly those specifications. The cost makes it attractive as well. As an added benefit, there are several protection features integrated into the IC. The most important one, it seems, is the overcurrent monitoring feature, which will be discussed later.
Being a mobile monitoring sentry, the battery is one of the most important decisions. Initially, we considered using a nickel metal hydrate battery. However, after further evaluation, we chose lithium-ion batteries instead. These are significantly smaller and more power dense, which is essential for our compact design. They also offer much more compatibility with wireless charging, which is one of our key stretch goals.
The change in motors made us need to increase up to a 12-volt battery, changing our selection to the Talent Cell 12-volt lithium-ion battery, which offers 11,000 milliampere hours. This battery supplies a stable 12-volt output that directly powers our motors, while also providing ample capacity to ensure that we get at least 2.5 hours of operation.
In selecting our 3.3 voltage regulators, we decided to go with linear, more specifically the S.E.E.M.S 1117. Following the datasheet, we found that it offers low noise output, which is perfect for components like our ESP32. In selecting our 5-volt regulators, we decided to choose switching regulators. More specifically, the MP2338 GTL, a regulator with up to 96% efficiency seen from the datasheet, and a compact design, ideal for our needs.
This diagram represents the core architecture of the S.E.E.M.S, highlighting the components and their connections and their assigned team members. Each block is assigned to a specific team member for development and implementation.
Having the sentry be autonomous is a large part of this project. Thus, we need to look into path planning and movement algorithms. As our system is a monitoring system geared towards movement in the environment, coverage is a significant parameter. The best algorithms to use fall under a class known as simultaneous localization and mapping, or SLAM methods. These algorithms form a map of the environment through sensor fusion and allow the robot to move through it almost seamlessly. They are typically very effective, but also very expensive, both computationally and financially, requiring quality LiDAR and quality cameras. Random walk is simple. Take the robot, send it forth in the environment, and allow it to make movements dictated at random. Perhaps counterintuitively, it is very effective at covering a majority of whatever environment it is implemented in. Bug algorithms simulate bugs in their movement planning and head towards a goal, only deviating when an obstacle is reached, at which point they direct the robot around the obstacle and back towards the goal. The algorithms presuppose a robot's knowledge of its goal and of its position. The random walk algorithm was chosen because of its high success at coverage and interior environments, low computational overhead and complexity, and low cost. The only downsides are obstacles, but this can be accounted for with sensors.
Choosing a programming language and an environment to build came primarily down to knowledge and comfortability in the workspace of the language environment. The selections narrowed down to React Native, Flutter, Swift, and Kotlin. Although Flutter is on the rise and seen as an attractive option to learn, we chose React Native with JavaScript and TypeScript as our main programming framework for our mobile application. Swift and Kotlin can be developed in their respective platform and exclude us from implementing the app in a cross-platform format. To produce a continuous stream of video over the internet, we needed to figure out what format are the video being transmitted in, and how do we obtain the video to display to our mobile application. Our options were the motion JPEG or real-time streaming protocol. The motion JPEG protocol streams every frame as a single image one after the other, in a seamless pace that appears as a continuous video. Our pick for the motion JPEG was complementary with our design, as we did not need to deliver audio transmission. In addition, the real-time streaming protocol will provide us with additional unwanted latency to the user screen. Moreover, the ESP32 CAM has built-in support for this format and allows of ease of integration of the protocol.
In code, the motor drivers will control the motors by taking in different combinations of PWM inputs. Alternating inputs allow motors to be off, turning clockwise, or turning counterclockwise. Pairing two motors in differential drive and driving them correctly gives movements in the cardinal directions. These PWM signals are provided by dedicated channels from Espresso's Motor Control PWM API. With the motor driver's current monitoring pin, we will dedicate a pin on the MCU to reading its voltage level. That level corresponds linearly to the amount of current that the motor is drawing. If the motor is deemed to draw over between 1 to 1.5 amps, the software will be set to stop the motors by disabling the drivers, thus preventing stall from being reached and lowering overall average power consumption. Output from the diagnostic pin immediately stops the drivers until software deems it safe to restart operation. The second diagram shows the general flow of communication between the MCU, driver, and motor. The sensor will collect data and information from each of the sensors and use that data to inform its decisions. The overall system will be task-based, but with the occasional interrupts for select sensor readings or timed events. Tasks will be created to collect data by polling each sensor at a constant predefined frequency and to communicate with CenturyLink through Firebase. The diagram shows an example data flow through the system from sensor to CenturyLink. As described earlier, the simple random walk method does surprisingly well at covering a space. It does very poorly, however, at avoiding obstacles. To combat this, the random walk implemented in the Sentry will use the included presence sensors for obstacle detection on top of the human presence detection. In this way, a virtual barrier is placed around the Sentry, not letting it hit anything immediately around it. To get the best randomness possible, we'll use the ESP32S3's true random number generator. It is based on hardware and randomizes numbers with respect to noise from the integrated Wi-Fi and Bluetooth antenna. The diagram is a flowchart on how the Sentry's random walk with obstacle detection is expected to work. To achieve the goal of notifying users of changes within their chosen environment, the Sentry will have an internal alert system run on customizable measurement thresholds. This system will interact directly with the Sentry sensors and with Firebase, updating the database whenever any anomaly is detected. An anomaly is a major change to one of the measures of environmental quality listed in the table shown here, and it is found by looking through recent measurement history within the code after each sensor reading. The second diagram is a flowchart describing how an anomaly might be detected. Here's an overall class diagram that represents the Sentry sensor and drive system. This describes modules created to wrap the functionality of each sensor and motor in order to make the system easier to work with by means of abstraction.
Firebase is our cloud service that will provide us the needs of storing and managing data from our robot to provide the information in the app. The most subtle feature of Firebase is the real-time integration that can instantly update the sensory data and allows synchronization with the app readings. Furthermore, the Firebase Cloud service provides us with an authentication that can handle user information with high level of security and encryption to prevent the user data being leaked. The communication between the Sentry and the mobile app will require a means to establish a connection between them. The Wi-Fi module will connect our microcontroller to Firebase to send the sensors information and retrieve them. On the other hand, the Bluetooth module will be similar to a one-time use setup to send the information of the Wi-Fi credential to the central robot to connect the module to the internet. An overview of the potential layout of our app here demonstrates our four main pages that we have in our app: the sign-in page, the main dashboard page, a customization tab, and the camera feed with the manual controls. The sign-in page will authenticate and certify the user's credential. With the dashboard page, it will show the user the sensor data report from the environmental sensor. Our customization tab will ensure that the user can change the level of however he or she wants the sensory data to be. The last tab will provide the user with a camera live stream when requested and the ability to move the robot around with the corresponding commands.
Our main PCB is a two-layer board measuring 146 by 156 millimeters. Down the bottom, you can see the barrel jack plugins from the battery as well as the two voltage regulators. To the top right, you can see our USB32, and to the left of that, you can see the USB and USB to UART options for uploading code. On all four sides, we have plugins for the four needed ultrasonic sensors, and then towards the top, you can see the connections for the microphone, BME688, and the ESP32 cam. For our breakout boards, we were able to replicate the designs of already obtained modules. We made the decision to slightly enlarge the PCB footprints and component placements on the BME688 board for easy assembly and troubleshooting. However, the motor drivers are limited on how much they can be scaled since they must plug in directly to the main PCB.
Here for our overall hardware schematic, I will point out the most important aspects of the circuit. Here's our 5-volt regulator and our 3.3-volt regulator. This allows efficient power going throughout our circuit design. Here for our overall hardware schematic, this is our MCU, our ESP32S3 schematic design. Here for our overall schematic, we have our USB and CP2102 programmer design. Here what's highlighted is our ultrasonic sensor connector pins from within our S.E.E.M.S PCB. Here we have an overview of our overall schematic for our environmental sensor. We decided to go with the BME688. And this is our breakout board design. Here's our overview of our overall schematic for our motor driver. We decided to go with the TB905 IFTG motor driver design for our breakout board from within S.E.E.M.S.
We use a 12-volt battery as a central power source, which not only drives our motors directly, but also feeds voltage regulators to supply our sensitive electronics. These electronics will draw roughly 600 milliamps at 5 volts. Each motor has a stall current at 5 amps. However, under normal conditions, we expect to draw around 1 amp, so the motors average about 2 amps in operation.
The first Century prototype was more of a proof of concept. It was built from cardboard and duct tape and ran a significantly reduced version of what S.E.E.M.S promises. A short clap or other loud noise would be detected by the microphone, simulating an anomaly. This would prompt the Century to begin moving forward. The Century would then move until the front ultrasonic sensor gave a reading that broke the default barrier around the Century, indicating that it should stop immediately. The second prototype will be built soon. It is to be made of 1/8 inch MDF laser cut to specification by the TI lab and then put together. Each system component has its dedicated place, with the battery going to the bottom level alongside the ultrasonic sensors. This is to ensure that the Sentry's sensor of gravity is low and that it can detect obstacles as low to the ground as possible, respectively. The PCB has a dedicated spot on the second level, and the third level is split amongst the camera and mic, with the BME having sole access to the topmost level. This prototype will be stronger than the first and is more representative of our vision for the Century as well.
This table shows our estimated total cost and budget set, as well as our total gross cost. It includes all the associated shipping fees and tariffs. As seen though, our total came out to be about $736, which is under our budgeted $900.
For our team distribution, Sprandio is our group leader and in charge of our embedded programming for the MCU and our motor drivers, as well as designing the enclosure design of our robot. Danny is focusing on validating the system and circuit components and supporting the PCB assembly. I'm in charge of the mobile app as well as aiding the sensory system and the mechanical housing design. Noah is responsible for PCB design and assembly within the addition of designing the power management system.
Here's our final progress table where we have completed all our milestone tasks that we set out throughout this whole project.
And with that, our presentation is complete. Thank you so much for watching, and please let us know if you have any questions.